Okay, good evening, guys. Uh, Last topic I'm going to discuss the assignment problem over here. And the assignment, the thing is, this assignment problem is a special case of the transportation problem. And in the assignment problem, I'm going to discuss the Hungarian method and the traveling salesman problem. The transport problem basically, we are going to think about the thing is that we are going to assign a particular task to the worker or a person over there, and the thing is this we are going to uh, this is work further going to link with the cost to complete the assignment over there, or sometimes we are going to look upon the profit maximization. That means there are the two things over there. One is the uh, uh, you can say related to the cost and time. Another one is the you can say profit maximization in the assignment problem. And we are going to assign the tasks, the number of persons and equal to the number of tasks over there. This I'll explain you in the coming slides over there. Basically, if I go with this, the whole theory part over there, there is basically you are going to the special case of the transportation problem. And the here the resources are uh, in the transportation problem. We see there is the supply centers over there is the distribution centers over there, and we are going to transport the product to the distribution centers over there. And in the transport problem, the matrix is of you can say 3 by 2 over there, uh, or you can say 2 by 3 over there. But in the case of assignment problem, every person is going to assign the particular task. So the this is basically a square matrix. Assignment problem we use a square matrix. The transportation problem may be a square or maybe a rectangle. Both type are possible in the case of when we talk about the transportation. And in over here, if I talk about the like m plus n, we already know where m is the number of rows and n is the number of columns in the transportation. But here, because same uh, uh, number of rows and same number of columns over there, so m is equal to n, so we can write over here is n instead of m. So n plus n we can say over here. And the objective over here is discuss that it is a cost, profit, or time. We have to see the things, and this is the optimization. We are going to optimize the things over there. And the problem may be of any type of this. So in the case of workers to machines, when we are going to production planning over there, then we can say this. We can use salesman to different sales areas, clerks to various checkout counters, class to the rooms over there, vehicle to the routes over there, contracts to the biders. So these are the things over there. And further over there, you can see this is the basic example of the you can say matrix of the uh, assignment problem. Here you can see here are the individual workers, and in this we can say row wise we can say this is basically the assignments. J1 is the assignment or activity, J2 is the activity, Jn is the activity. We are going to allot, and this allotment is basically we are going to think about the how much we are going to allocate, which task we are going to allocate which worker. So this is all about, so to get the uh, cost minimum or time minimum or profit maximum. So over there we can write in this form also. Here xij represent the assignment of resource, and assignment of xij and I we know, and j we know, I we in the row wise, and j is the column wise, and I is the you can say facility, I to activity j, and I is this is the workers, and j is the your assignment summary. So in the assignment problem, this is special case over there, and in the assignment problem it is a one, otherwise 0, because if suppose worker 1 is going to assign uh, this this worker 1 is assigned this task j2, that means it is the one by one, rest is we are not going to consider. Rest we are not going to, suppose worker 2 is going to assign this, so we can say this is 1 on 1 over there. So that means if resource I is assigned to activity j over there, then it is 1, otherwise for all other it is a, we can say 0. And further we can say the instead of transportation problem we see the number of units going to have the warehouse, and number of demand the number of units demand at the demand centers in the transportation problem. But in the case of assignment it is allocated 1 over there, because when one worker is assigned a assignment, so that means we it is a only one assignment is going to assign a particular worker, or one particular assignment is going to assign a particular worker. So vice versa it is a 1 over there. That's why you see the one number over there is there. And further we can say as we already study in the terms of in the LPP, we have the equation maximization or minimization. Here it is a minimization, we cost and time, we talk about in terms of cost and time. So it is a z minimum function is there, and z minimum Cij Xij. Now Xij we already think here it is a 1 over there. So Xij is 1 for all i's, for all I and for all j, and for all i's, for all j's over there. So it is a 1 over there. These are the constraints, and we can see this is the special form of the linear programming problem over there. And Cij, what this represents, the coefficients in this matrix over there, this is represent the cost to assign a particular task to the worker. And further as we already see, uh, the assignment problem can be further solved using the simplex method, using the transportation method, using the Hungarian method. Now let's check what about these, why we are not prefer the simplex method. In the simplex method uh, we are going to as we see in the assignment problem can be formulated 0 to 1, we already see either 1 or 0. This we see in this part over there. This when one assignment is assigned to one worker, that is a 1 over there, otherwise 0. So that means it is basically 0 1 over there. And and such problem can be solved by the simplex method. But the thing is this, the general mathematical model in the assignment problem is n cross n. In the simplex we see m cross n is the number of decision variables, and in the case of assignment it becomes, because m is equal to n, so it is a n cross n decision variables. So how many decision variables we have? So all are decision variables if we see over there. So these are the n decision variables are there. And now how many inequalities? It is a n plus n, that means 2n inequalities over there. So assignment problem, if I talk about for any assignment problem that involves 5 workers and 5 jobs, that means matrix will be 5 into 5, 5 cross 5 matrix. So how many decision variables we have? That means in the matrix we have C11 to C55. So that means these are the number of decision variables. Which variable we are going to allocate? Which variable is going to associate to reduce the minimum cost or minimum time? So these are the basically decision variables over there. So how many variables are there? 25. And how many inequalities? Because in this side there is the 5 workers, and over this side there are the 5 assignments. So total, if I want to write the in terms of inequalities, then that means 5 for the workers, 5 for the assignments. So it will come to be 10 equalities over there, and it is very difficult to solve this type of this huge number of data when we have suppose 10 by 10 matrix over there. Then it is very difficult to solve manually. If we go to the transportation problem, then in the transportation problem we generally use the Modi method over there. And in the Modi method we see for the every basic feasible solutions we come to the scale matrix over there and order n over there. And in the Modi method we check that when we are going to find the optimality test, we perform the feasibility over there, then m plus n minus 1 is equal to the m plus n minus 1 is equal to the number of allocated cells over there. And if I talk about in the assignment, that m is n over there, it comes to be n plus n minus 1, and it is be 2n minus 1. But here the assignment is problem is have the special structure over there. And special structure means every worker is going to assign one particular task over there. So this basically comes to the uh, because in the assignment problem it is not going to be equal to the number of allocated cells. This m plus n minus 1 is not equal to number of allocated cells. That means it leads to the degeneracy. This leads to degeneracy, and to remove the degeneracy we have to add the dummy row or the dummy column over there. And in the case of we already see that we have added the epsilon term to make the uh, non-degenerate solution over there. So if I go with this, that means, but here the allocations you have to made a lot over there. So that means it is very difficult to solve this assignment problem uh, with the Modi method, because here the you have the due to this epsilon over there. And now come to the assignment problem for the this solution over there, feasible solution over there. Now we go to the Hungarian method. In the Hungarian method, this is basically the flow chart, and in this first we have to arrange the matrix in uh, the statement into the matrix form. And in the matrix form, when we write, is it a maximization problem or a minimization problem? If it is a maximization problem, we can write we convert it to the minimization problem, right? I'll tell you what we have to do. And suppose this is the minimization problem. Suppose this is the minimization problem. Then yes, we can, if because it is a maximization problem, then we convert it to the minimization problem. If already it is a minimization problem, then we continue over here. Is it a balanced problem? If it is yes, then we proceed. If it is no, we are going to add the dummy row or the dummy column. And after that we are going to follow, this is the basic steps of the Hungarian method. I'll tell you what these methods are with the help of example. Now, so I'll take this example over there. And in this example, we have to find the assignment. We have the problem, assignment problem. Assign workers A, B, C. These are the workers, and these are the assignments. And assignment is going to put over here, and workers is going to put in the row wise, sorry, column wise, and the assignments will write in the column wise over there, this way. So our aim is to reduce the total cost. That means problem is the minimization problem. We start from here. So very first process is the, we have to, there is a two basic things are there. We have used the row reduction, and the column reduction. This is the very first step. Very easy. This is very easy. Column reduction means we are going to first concentrate on the only rows, and then we concentrate only on the column sides over there. Now in the row reduction, we are going to check those coefficients which is having the least value in the rows. In the case of this, if I talk about this over there, in this row least value is 3, in this least value is 2, and then over this, for this row least value is 5. So what we have to do, subtract this 3 from this and this coefficient from 6 and 5. So it comes to be 3, it comes to be 0, and it is 2 over there. And further, it is the minimum value is 2, so subtract this from 5 and 9. Your answer comes to be, your value comes to be 3 and 7. And then from here it is 5 minimum value, and then we are going to get 7 and 8. And it is a 5 minus 5 becomes 0, and it is 2 and 3, like this. Further, now it is to be comes to the, we write the zeros over there. These are the zeros we get. These are the zeros we get. Further, we are going to do the column wise reduction. In the column wise reduction, we now look upon the after row, first row reduction, and then we use the row reduction matrix for the column reduction. After same this matrix we are going to use, and further we'll do the column reduction. In the column reduction, we are going to check it out the minimum values over there. And in the case of this, now look upon there. Now there is a 0 in this matrix. There's a 0 over here. There's 0 over there. When we look upon the column reduction, we do the column reduction. We are going to check it out the minimum value in a column, and it is a 0. Here it is a 0. So we subtract 0 from 3 and it will remain same. Subtract 0 from 7 to it remains same. Subtract this 0 because it is a minimum value. It is 2 and 3 remain the same. So at the end, after doing the column reduction, we are going to get the nothing is be changed over there. So that means 0 means what? That means this is the assignments we have done. That means for worker A, the assignment we have done is, that means if I write over here, A is assigned second job, and B is assigned third job, and C is assigned first job over there. And then we can find the values of the each cell over there from the original cell. So A is assigned the cost for this cell is 3, and cost you can compare B3 C1. So you can find over here when you are going to assign all the jobs over there, then you sum up this and you get the 10 rupees cost over there. So that means worker A will do the job 2, worker B will do the job 3, and worker C will do the job 1 over there, and total cost of your assignment will come up to be 10 rupees. Okay. Further, there is another thing we have look upon the degeneracy. Degeneracy over here, we see, I'll take the example over there. This is basically, if I talk about, this is the matrix of, this is a 5. There is a, how many 5 jobs are there here? Workers are 1 2 3 4 5 5 over there. That means it is a basically square matrix 5 by 5. Now first we have to perform the row reduction, and the row reduction we look upon this row, minimum, this row, minimum value, this row, this row, this row. In this row, very first row, the minimum value is 2. This is the minimum value, and in this row minimum value is 2. In this row, third row, the minimum value is 2, and fourth row the minimum value is again 2. Fifth row the minimum value is 6. So we perform this. That means subtract 2 from all others, from all the row elements over there. So 2 minus 2 becomes 0, 0, and 3 minus 2 becomes 1, 8 minus 2 6, likewise 10 minus 2 8, 3 minus 1 this. Similarly we have to go with this, subtract 2 from all other elements to get this value. And for third row, subtract 2 from all other row elements to get the value of this. Similarly for fourth element, subtract 2 from all other elements to get this row elements. And again at the end, for fifth, subtract 6 from all other. 6 minus 6 becomes 0, 6 minus 9 3, 6 minus 10 4, 9 minus 6 3, 10 minus 6 4. So this is the column, we have done the column reduction. And now use this row reduction matrix in the further column reduction stage. Now in the column wise, we look upon this, over there. In the column reduction, we are going to look upon, this is the first column, this is second, this is third, this is fourth, this is fifth. So in the first column, look upon which is the minimum value. Here the minimum value is 0. Here the minimum value is 0. Either both are minimum values. and further here the minimum values all are 0. Fourth one minimum value is 0, and then fifth column minimum value is 0. So we are going to further uh, put the values over there. Now in this case, this rule we are starting from. That means we are going to priority the things like this. We are going to see the unique zeros alone in the row and column, single zeros alone in the row or column, and further we have minimum zeros. So these are the important, you can say, things we are going to consider. In the case of this, now alone sorry unique zero alone in row, and this is the and means both row and both column we have a zero over there. Single zeros alone, or single zero in the row or in the column, and then we have to find the minimum zeros over there. With this I'll show you this. Now over there, if I start from this, if from start from this row over there, now you see here 0 is there, so we assign this 0, right? We are going to pick this, and we are going to other we are going to these are the, because 0 is already being marked over there, then it is a being assigned. And further you see in this, if I look upon this, if I go with this, that this and this and this, here there is a 0 over there. 0 in the row is there, and 0 in the column. There is a one zero, unique 0 is there, right? And that means this we are going to assign. Next we see the next row. In the next row we can see this is the 0. We look upon the zeros over there. So this 0, when we look upon, this is the 0, and in the row, and to the column, this is the column. So this is the 0 we are going to assign. That means assign, the thing is this, that means the this square box means this is the assignment to that worker, to that particular worker, to that particular job. This is the meaning of this. So over there, if we going to select this, because there is a 0 over there, and all other zeros you can cross out over there. And further you see, in this case, you see, because this is cross out, this is cross out, this is cross. Now this is the case. So in the third row, this 0 we are going to assign. Similarly for third row you can see this is the third row, and this is my column. So this is means this condition is satisfied over there. Row and column is having at least one 0, unique 0 over there. And now we look upon this fourth row. In the fourth row, this 0 is, you can say, cross out, because we keep this 0 and all other zeros will cross out. And in the fourth row, now this 0 is left over there, so we assign over there. This is the assignment, and then further we look upon. Now if you go with the fifth row, now this 0 is already crossed out. That means here no 0 is there, no 0 you find over there. So that means at least single 0 over there, right? And this 0 is already been crossed out, so we are not going to find any 0 in the row 5 or row or column 5. So that means when we that means nothing to be assigned for this row 5 and column 5. So that means if I check the assignments over there, that means this is A, B, C, D, E. So that means A is assignment, B is also assigned a job, C is also assigned a job, D is also, but here D has not been assigned any job over there. You can see it. So that means this is called the degeneracy. When you have the number of allocation, when you have number of allocations of jobs to worker is not satisfied. That means you see here is 1, 2, 3, 4. 4 is there, and how many workers and jobs are there? 5. 5 workers, 5 jobs. So this condition is called degeneracy. How to resolve this? How to remove this degeneracy? Now in the case of degeneracy, now I take the last this column reduction matrix over here, and then I try to remove this degeneracy. Now to remove this degeneracy, uh, first we have to look upon the row or column which is having the highest number of maximum number of zeros, maximum zeros, maximum number of zeros. So for maximum number of zeros, you can see this is the column which is having the highest number of zeros in the column. All are zeros. So we cross this. We draw the line. We draw the line. Now next we look upon the this here in this row. Sorry, in this column only one. In this column only two zeros over there, right? And in this we look upon 1 0. In this column we look upon only 1 0. If we go with this, there is the 1 2 3. That means we can cross this. If we look upon this row, only 1 0. If we look upon this, there are two zeros. Draw the line. If we look upon this, there are the 1 2 3. Three zeros are there. Here only one. So we are going to cross this. The thing is we are going to cross in such a way that with the single line you can cross the maximum zeros over there. If I draw, I take the example over there and draw example. Suppose this is my square matrix. This is my square matrix, and here suppose this is the 0 0 0 0 0. Here I write any number of 6 5 3 2 over there. Now, and suppose I have made assignment this. That means rest of there are 0 0. 0. So how many lines I am to use to cut these zeros? One line and another. That means with the two lines I can uh, cross all the zeros. So and this is the case over there. Similarly, if the zeros are like this, if zero, so this is the case. But means if zeros are in line over there, zeros are like in line over there. So this is the case. 1 0 must be there. So this will be crossed. So this way I can cut the zeros over there. Now further is this, basically to remove the degeneracy I have to draw the vertical and horizontal lines. These are the vertical and degeneracy to the vertical and horizontal lines. But to cut the zeros, right? And further you can say over there, if I see in this case, now what we have to do further. Now, in this matrix we see there is a uncut cells. These are my uncut cells. These are my uncut cells. These are my uncut cells. Another is this uncut cell, uncut cell, uncut cell. Any other? Right. So these are my uncut cells. First we have to do, first select the uncut cell and subtract the minimum value of uncut value. Now 5 3 6 4 2 2 2 3. In this, which is the minimum value? 2 is the minimum value. Further, for the cut cells, these are the cut cells. These are the cut cells. So for the cut cells, we are going to simply copy and paste. And then for the intersection, these are the intersections. Intersection elements, we are going to add the minimum value of uncut. That means at the intersection, we are going to add, we write the 2 because 2 is the minimum value for uncut. So our matrix will look like this. So this is the I put first value over here. This is my uncut uh, coefficients we put in the matrix. You can see it is I think 5 is already been cut. Okay, okay. The thing is this 5, 3, 6, 4, and then 2, 2, 2, 3, and minimum value is 2. What we have, right? Subtract. We subtract this from 5 to, when you subtract 2 it comes to be 3. For 3 subtract 1, 6, 4, 4, 2, it is 2. It is 2 minus 2, 2 minus 2, 0, 0, 2 minus 2, 0, 0, 3 minus 2, it is 0. This is how we can uh, uh, mention over here. Further, further we can see this. Second step is copy the cut values. All cut cells we put over here. Same, you can say 0, same 0. I put 4, 4 over here. So you can see out this. You see, these are my cut cell values. 4, uh, here 0 is for the intersection, so I am not going to put the 0. 7 uncut, sorry, cut cell. 0 is the coefficient of cut cell, and then 3, 1 is the uncut. Now next is 3, 0. Again this value is intersection value. 0 is the cut cell, and then 4 is also a coefficient of the, then 2, then 5, 0, intersection. Next is intersection. This is the cut cell. This is the cut cell. This is the cut cell. So yellow highlighted cells are cut cells, and the values 3, 1, 4, 2. This value 3, 1, 4, 2 is the, these are my these are my cut cells value. Now, what about the intersections? Now this is my intersection area. This is my, sorry, this is not. This is the intersection. This is again the intersection. Now, how many intersections? 1, 2, 3. So these are the 3 cells. Uh, Empty cells are there. Now we put the intersection value. Now add the minimum value of uncut. Uncut value is, I already told you, it is a 2. In uncut all coefficients, the minimum value is 2. So we put the 2 over there. When you put the 2 over there, uh, you see this is the intersection. You put 2. Why 2? Because the least value of the uncut cell. And then intersection element is, this is also intersection. This is also the intersection. Further, now after that it is very simple. Now, over there, this table we have it. This is the table we got. Now further we are going to use this priority system over there. Now first you see in this section and in this section, in this row and in this row. Now we check zeros row wise and column wise, right? This. Now if I consider this, suppose I start from here, I'll show you this. So if we look upon there, if we look upon the column number 3, if you look upon column number 3, the 0 is there. So you are going to look upon this. This is my row, the 0 is there, and this is the column. If I going to assign this 0, that means other 0 is going to automatically cross out. Similar way we are going to do with other cells. For other cells, if I go with this is already assigned, this is cross out. Further we are to this I going to assign, and this will be it is up to you. Suppose I do this. Basically, it is a iterative process. Iterative process. So in the iterative process, you do by your own. At the end, the thing is this: if you are not going to select the optimal path over there, then you might take a more time, but ultimately you reach the your target. So over there, if I go with this I have assigned. Suppose I go with this. Suppose column wise I can go. If I go with this, suppose I assign this. For the this column, there is a 1 0, and for the row 1 0 I have assigned. So remaining 0 we cross. Now we go with this. This 0 I have already been assigned, and this 0 is already been crossed. Next we go with this row 3. And this 0 you assign, this 0 you assign. That means, and for column this is crossed. For this row, this 0 is available. So you check this and you cross this. You have assigned. And for this row, 1 is left. So you assign this, and all other are already crossed. So that means this is the assignment you made. That means if I compare this to this value, you first see. That means this 0 we have assigned. That means this. That means A is assigned J, and then we have 0 over there. It is basically B. If I A B C D E, and this is F G H I J. So that means B H. Worker B is assigned H job, and if I C worker is assigned G job, D worker is assigned I job, and E worker is assigned F job. So this is how now we can easily now this here when you count the number of zeros, how many zeros are there? 1 2 3 4 5. That means now it is the degeneracy is removed, and now your solution is you can calculate from this matrix, and this from here the total cost for the assigning the job comes out to be 21. Right? This is how we can remove the degeneracy, and we can solve the our assignment problem if there is a degeneracy in there. Further, if there is an unbalanced assignment problem, unbalanced means you have as a number of rows and number of columns I have told you, but if the number of rows are not equal to the number of columns, right? Five workers, sorry, 5 jobs and 5 workers. Right? Number of columns and number of is 5 cross 5. But if it is not so, that means this will become the unbalanced assignment problem. Similar way in the transportation we see the number of allocations over here. If some of this and some of this, in the case of these are the distribution center demands, these are the demands over there we write over here, and these are the warehouse capacity. And if warehouse capacity is not equal to the demand, or either way you can say, if demand is more or less, then we can write a unbalanced transportation problem. And to remove the unbalanced transport, we generally do the we are going to add the dummy row or dummy column. Similar way, in the case of assignment problem, if it is not going to be equal, uh, row and column is not equal, then we are going to add the dummy row or dummy column with the zero cost over there, and make it a square balanced matrix. We can see over here, this is the minimization problem, and here is a first column, second, third, fourth. It is a 4, and here it is a 5. So that is a 5 cross 4. It is not going to be equal. So we are going to add the another dummy column over there, and dummy column value we put 0. This is how we are going to solve. And then we make it a 5 cross 5. Now 5 workers, 5 jobs are there. One is dummy, and then we can easily solve. We are going to convert the row reduction, and the row reduction we can see over here. In the if I go with the this row reduction, then this is a 0, this is 0, this is 0, 0, 0, 0 over there. So 0 minus coefficients, the value comes to be same. But when we go with the column reduction, in the column reduction we see, in the column reduction, the least value in this column comes to be 7, in this least value comes to be 12, in this column least value comes to be 18, here 15. So it is 0, 0. And then after in the column reduction, what we do, we are going to reduce the minimum value to all other elements. So it comes to be 7 9 minus 7 2, 7 minus 7 0, 9 minus this 2, 10 minus 7 3, 10 minus this way. This is basically you are going to, after row reduction we go to the column this way. So this you are going to get, and then the updated from here, this table we get, this is the table we get, and then after this is your updated table. This is the final table you get, and then we have to uh, uh, we are going to assign the zeros. Now the assignment of zero is this. Suppose we are going to go with the row wise, column wise over there. Just come to straight away over there. Suppose I come to this part. Suppose first row is this. In the first row, what we have to do? There is a two zeros. We have assigned this. When we assign this, now how to check this zero is okay. In the row, I have told you, and the unique zero in the row and column both are. That means this row have 0 and this column is also have a 0. So this 0 we are going to assign over there. Second, now look upon this row, worker B. Now worker B, we come across this 0 over there. So in the column there is a 0, in the row there is a 0 over there. Other 0 we cross. Other 0 we cross. So we assign this 0. In the case of C worker, there is a, you can say 0 is only in the dummy. So we assign this. This is cross, this is cross. So we are going to assign the 0. Further, in the case of D, we look upon the zeros. We look upon this 0. So in the column wise and in the row wise, you have the 1 0. So we assign this 0 and then other 0 cross out. In the E row, you can find, we are not going to find any 0 over there. So that means if I going to count the number of zeros, A we have assigned A, assignment 4, B assignment 1, C we look upon the assignment, we have given the assignment J5, D we have given the assignment 2. What about the E? That means E do not have any assignment. We have not assigned the any job to the worker E. So that means this solution is not an optimal. That means it is a degeneracy. So further we have to remove the degeneracy over there. This I have already told you how to remove the degeneracy. Look upon this. This is how to remove the degeneracy. These are the 3 steps to remove the degeneracy. We look upon the uncut cells. We have to means uncut cells means we have to draw the horizontal line and vertical lines to cut the maximum zeros. Now I'll show you over there. Now these are the zeros. First maximum 0 you find in the J5 column. This we cut. Further, we in the row wise we find this 0, 2 zeros are there. Draw, cut this 0. In this 2 zeros over there, cut this. In this only 1 0. Here you get the 1 2 3 0. Draw. here only one. So the uncut cells, these are the uncut cells. These are the uncut cells. These are the uncut cells. And now what we have to find? The minimum value. Minimum value is 1 over there. And then subtract this one from all over there. You can see. You can check it out. 2 becomes, I mentioned over here, 2 becomes 1. 6 becomes 5. 3 becomes 2. 3 becomes 2. You see 1522. 1522. And over here it is a 2 2 2 0. You see 2220, right? And then paste the cut cells as it is. Paste the cut cells as it is. These are the, not the, we are not talking about intersection. We'll look upon the intersection later, but just as copy paste as it is, uncut cells. And then we paste over here. And for the intersection, I told you, for intersection, paste the minimum uncut value as it is. So we add the all intersections, put the values over there. This is one intersection. You see the one is there. This is also intersection, one value. This is one. This is again intersection, one. So there are three ones are there. Three ones are there. One, 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 one. Now again go to the row reduction and the column reduction. And in the row reduction, column reduction, we are going to look upon there. Now first, this is the row, this row, this row, this row. Now first we look upon this. Here you met the 0. In the column, 0 is there, other 0 is going to be crossed out. So this is it. Next row you go. This is the 0 you find over there, and also in the column it is there. In the third, it is a 0 over there, and in this other 0 if you point, cross out. And in the third, the fourth, there is a 0 over there. Assign this, and other 0 you cross. And similarly fifth, you find the no 0 over there, right? In this case. Now further you are going to assign the things. Now over there, because it is not, again you see how many assignments are there. You have made assignment 4, but worker are 5. So again you do the degeneracy. Draw the lines, cut the lines, cut the maximum number of zeros over there, and then paste the uh, uncut after subtracting the minimum value of the uncut cell, and then paste the cut cell as it is, and the intersection points the minimum value. This is the intersection point, the minimum value of the uncut cell. So that's why you see 4 becomes here 5 over there. You see this. Here is a 2 uncut 2, 1 1 5 2 2 2 2, and this, yes. So intersection B and 4, B and 4, here B and 4, just a second. Yes, the thing is this, we are going to do the we uncut. First look on the uncut cells, and in the uncut cells we are going to subtract, and we are going to subtract the things over there. Then you are going to see the your minimum value is 1. So here you subtract the 1 from the 2. It is 1 1 0, becomes 0. 1 minus uncut cells, it becomes 4. This is 1, this is 1, this is 1, this is 1. So this way we write the uncut cells over there, and then we are going to copy paste as it is cut cells. 0 5 2 4, 0 5 0 0 5 2. This is the intersection element, and then we have the another intersection element, this and then this is the also intersection element. That means 0 0 is the intersection element, then again this is the intersection element. Now in the case of this, there is the if 0, no, in the intersection element what we have to do, we have to add minimum value of uncut cells. Add. So 0 plus 1 is equal to 1. So this 0 becomes 1. Here it is 4. That means 4 plus 1 becomes 5. Here 4. 4 plus 1 becomes 5. That's the thing. That's the here you get the 5 over here. Here you get the here you get the it should be 1 over here. No, it is not. It is the intersection. No, it is not intersection. It is not. By default I counted the intersection, but it is not intersection. So it means it is as it is. It means as it is. So now we are going to check the we are going to allocate the zeros. Again we see row, this row, this is there, in this row this is the 0 we get, in this 0 we sign, again this 0 we sign, and this 0. Now you get 5 assignments to all workers. So now you have been get the final optimal answer. So optimal answer, then you get the corresponding cells, you put the values over there, and sum up this, you get the optimal cost. This is how we are going to solve the unbalanced problem. Further, in the maximize, if the problem is instead of minimization, you have the maximization problem, then what we have to do, instead of subtracting the minimum value, now we are going to subtract the maximum value in the case of row reduction. Or that you can see. I'll show you. Yeah. Now you see. Now we have the subtract the values. Now what value? Now subtract the maximum value. This is 42. Now 42 you are going to, this is the row, sorry, this is the column over there. Now 42, from this it is the 12, this is again 12, this is 18. So this is the we are going to get. Similar way we are going to subtract the maximum value. Here is 35. You subtract the just give me a second. Yes, subtract the this highest value, subtract the maximum value from all cells, from all cells coefficients. So 42 you are going to subtract from all cells, and you get the this value. You are going to get the value of this. After that, now you are going to do the row and columns, row reduction and column reduction over there, and then you are going to, again the formula is same. After that it is very, after that it is simple. When you are going to convert the maximization problem to the minimization problem by select the maximum value from all the cells, then subtract the maximum value from to the all the cells, then the again we are going to follow the row reduction formula and the column reduction. From the row, select the minimum value and subtract, you get the zeros over there. This is how this is 0, this is 0 over there, this is 12 value, this is 12, and this is out of this 18. So this will become 0 in the case of row reduction. And then we are going to see in the column reduction, we are going to do the column wise reduction over there. And after that we check whether it is a optimal or not. And in the case of this we see this, we are going to see the zeros over there. How many zeros we are assigned? 1 and 2. Now how many workers are there? Workers are 4, jobs are 4, but the thing is this, we are only A is getting assignment and D is getting assignment. B and C is not getting any assignment over there. So this is not the optimal solution. That is the degeneracy. We have to remove the degeneracy, and the degeneracy we are going to remove using the same thing. The using the uncut cells. Using first uncut cells, we consider the uncut cells, and then from the uncut cells we find the least value, and Then we subtract the least value from all other values, and then we put over there. Second, we are going to use the cut cells. Cut cells paste as it is. Then intersection. In the intersection, the least value we get the intersection elements we are going to add and write. This way we are going to get the values. Now after do this operation, after do this operation, we are going to now again we check the zero, that unique zero row and column, and single zero row or column. This we are going to check, and then we are going to cross this. Now you see 0 is assigned, this is assigned. Now B is getting assignment, D is getting assignment, but C is still not getting assignment. See, that means solution is still not optimal, and then we make it a optimal. That means it is a degeneracy, and then we make it a degeneracy again. We have to solve this again using the uncut, cut, and intersection elements. Right? And then we check at the end, we get the all assignments and all workers are going to be uh, balanced over there. Now all worker is getting the assignment, and then we are going to check the respective cost over there. So from there we can easily uh, check the cost, total cost to assign the particular job to a worker. So this is the least cost we get 99. It may be a units of rupees. Now, the last topic of this is the traveling salesman problem. Traveling salesman problem basically is that there is a person who has to go to the different cities. In this salesman go to the this is the factory. This is the distribution centers. Factory means suppose he has to move from suppose city A, city B, city D, and this is A, B, C, suppose D. This is the now salesman has to follow which route so that you are going to get the uh, reduced cost or reduced time over there. So we have to think about in terms of minimization of the problem. And in the case of salesman, again the thing is this 1 0 problem is there from I to J. That means if the salesman is go from A to B, then we get 1 over there, and if we get go to the A to A, then 0 otherwise. Like this I told you as an example. You can check it out. And now, this home city. I'll explain at the end of uh, this problem. Now we start with this problem. In this problem, this is the matrix shown. The infinity means this is the restricted path. Means the thing is this, in the salesman problem, the sales per salesman is going to cover all the cities, all the five, A, B, C, D, E. So we have to choose the path. Suppose A2 first you go to B, then B to D, suppose suppose then BC, this B to C, C to D, then D to E. Suppose that means A to B he go, then B to C, then B to C. Like this, we are going to check whether this path is optimal or not, and at then A and E to A. That means it is basically a closed loop system over there. And if I there is a restricted path over there. That means from the same city, if he go, that means his path is going to be closed. That means he is going to, without going to any other B, C, D, E, his path is going to be end over there. So that we are going to restrict. That's why you find the infinity signs over there when A to A, B to B, C to C, and the D to D and E to E over there. So this is why you get the things over there. So now you can note down the things in this I mentioned over here. Need to we have to need to prepare it that we can visit all 5 cities at minimum cost. So this he has to visit all cities with minimum cost. Minimum distance may be minimum time it may be. Now the infinity over here. Infinity means it is a restricted or you can say block route or prohibited route. This infinity means the block route. He is not going to allow to follow A to A, B to B, C to C, D to D, and that means same route over there. And then we start how to start this thing. You see, this. For first thing, as we already do, row reduction. We do the row reduction. In the row reduction, we know in this row, in this row, in this row, we find the minimum value. In this row, 2 is the minimum value. First row, we find the minimum 2 is there. Second row, we find the minimum value 2 over here. This is third row, we find the minimum value 3. Fourth row, we find the minimum value 2. Fifth row, find the minimum value 3. So, what we have to do in the row reduction, subtract 2 from remaining all this, from all elements of the row 1. 2 subtract from this, and then third row subtract 3 from. That's why that meaning of this, you are going to get the 0. This where there are minimum value, you get the 0. You get the 0. This is a row reduction, and then use this table to further column reduction. In the column reduction, what we have to do, we check in the column the minimum value. The minimum value over here, we have the 0. See, as it is, no change over there. In this B, minimum value is 0, no change. In the C, you look upon, there is no 0. That means now look upon other elements. 2 is there. So now 2 becomes 0, and now subtract 2 from all other column elements. So this will become accordingly. 4 becomes 2, 6 becomes 4, 6, this 6 becomes 4. Further this column, you get the minimum value. Minimum value is 0, 0 minus 6, 0 minus 5, 0 minus infinity, 0 minus 8 means same. For this column, there is 0. So 0 minus 3, 2 minus 0, 3 minus this remains same. So you get the column reduction matrix over there. Now, after that, we look upon the penalties. For the penalties, you have to remember that this penalties over there means uh, penalty we have to avoid, and if it is maximum, then we have to assign the root first. So if I look upon the penalties, step 3, now find the penalties for each 0, only for zeros, not for any other element. So when we look upon the penalty, this means minimum in the row and minimum in the column we add up. I'll show you how. If I look upon this row here, if I look upon this 0, if I look upon this 0 and this column, here the 0 is there, here it is 0 in the row. This is row. Other element is 0. That means in the row element value is, if I write 0 plus, in the column minimum value is what, 4. That means penalty becomes 4. Other, now look upon the C, A and C. So in the C, we look upon here. It is a how much value it is a, you can see 2 over there. 2 is the minimum value. So it comes to be other values 0. So it comes to be 2. Like this way, we are going to write all the penalties for all the zeros. So you can see for 4 I mentioned 0 plus 4 for this, because here minimum value in the column is 2, and in this row the minimum value is 0. For this for this 0 for this 0, the minimum value in the row is 1, and the column wise minimum value is 2. For this 0, the minimum value in this is 2 in the row, and column wise minimum value is 5. So 5 plus 2. And for this row, for this row and for this 0, the minimum value is 1, sorry, 0 is there, 0 plus, and this column minimum value is 3. So 3 is mentioned over there. Similarly for this and this, 0 plus 4, 4 is the minimum value, so it becomes 4. This is how we write the penalties. Now that means if I write over here this, now here maximum penalties, what is the maximum penalty? Here the maximum penalty, if you look upon 7, and this is the maximum penalty we have checked. And over there, if I that means if something gone wrong, if something is going to be wrong over there, then the penalty will be maximum over there. So we have to be assigned this cell very first. We have to priority to assign this cell very first, so to reduce so that this thing is not going to be happen, that otherwise our cost of traveling cost or time, or you can say distance, will be increased. So we have to assign this in the next table actually. So we assign this, you can look upon there, this is the assign we have assigned. That means a route comes to be, that means this route is fixed. What route is fixed? C to D. That means this route is now fixed. This route is now fixed over there. Whenever salesman lands in city C, he always go to the D city. That means whenever he goes to the city C, he further go to the city D. It is not like that if he land in the city C, he go to the A or B or D or E. He must first, after C, he go to the D. That's the meaning of this. And whenever we have assignment made over there, C and D, that means it is going to remove permanently. That means this is fixed. That means C row is fixed and D column is fixed. That means now we no need to further evaluate this row and column. So we remove this. We are going to remove this. You can see this we have crossed out and we remove this. Further, that means we have to block the also reverse route over there. And to block the reverse route, how to do this thing? This is a very important step. And to block the reverse route means it is like this. C to D is fixed, but what about D to C? That means we have to fix this. We have to block this. C to D is the route is fixed, and D to C we have to block this, because if we get the optimum solution, we get the optimum solution in D to C. Salesman go to the go to C to D and D to come back C. Not want to come back from D to C. Hence, we can say route is blocked. Otherwise, come back home by only visiting two cities rather than he want to visit all five cities. Rather than he cannot visit all five cities over there. You got my point or not? If we are not going to block the C, if we go to C to D and then come back D to C, come back to D to C over there. So that means all other routes are going to be all other cities are not he is not visited. So that's why we have to block. That means C to D he can go. That means after D he go to other city. It's not like that from D to C D he can come back. So when we block both ways, that means now he has further moved D to further any other city. That's the thing. That means we have to block the reverse route. And to block the reverse route, we have to mention that table like this. You can say this is the infinity over there. This is the infinity, and this infinity we have to mention. This is the now C row and D is going to be removed from the matrix, completely removed from the matrix. Why? Because we block the whole route, whether he is going to C to D or D to C. We have removed. Now, in the case of this, you just look upon in this column, D will move. In this column, you see no D is there. In the row side, you see no C is there. In the row side, no C is there. So we remove the D. And rest of the infinity, the restricted path values you first write over there. Now we have see the things over there. This is our initial after row reduction we get the column reduction values, and now we uh, paste all the values over there because this is removed, this is removed, and C is removed. So we are not going to this. Rest of the values 0, 0, 3 we write. Now you can say this is the only problem where your matrix is going to be reduced after every step over there. Now you see. Now matrix is going to be reduced. Now it becomes instead of 5 by 5, it becomes 4 by 4 matrix. 4 by 4 matrix. So now we have to check this. This is the 0, 0, 3, 1, 2, 0, 0, 4, 3, 0, 4, 4 infinity. So this is our reduced matrix. And then again we have to do the row reduction in this. Row reduction and the column reduction over there. Row reduction we use and column reduction we are going to use over there. And in the then we use the penalties over there. First we do the row reduction. In the row reduction we are going to, because here it is in the row this is 0, so not going to change. Here again 0, not going to change. Here is 0, that means not going to change any value in the row reduction. 0, no, not going to. Here in the column wise you see there is a 0 over there. Here 0 is there. So that means this column remains same. 0 is there, no, not any value is going to change. In this column reduction 0 is there, 0 is there in this, so value remains the same. After this row reduction and column reduction, what we have to do, we are going to assign the penalties, and the penalty is basically the minimum value in the row and the minimum value in the column only for zeros. So we have checked this is the 0, we have checked this 0, and when we check this 0 we are going to look this. That means if I going to this 0, look upon this row. After 0, what is the least value? 0 is there. And in this column, the least value is 4. That means 0 plus 4. This is the penalty. And for this row, 2 is there. You can see 0 plus 2. That means 0 plus 2. Here 2, here 0. 0 plus 2. Further we look upon this. Here 0 is there. Yes, 0 is there. So we look upon this. Here the minimum value in this column 3, and over here the minimum value is 1. So 3 minus 1, this it comes to be 4. comes to be 4, comes to be 4. Yes, come to be 4. Now further, for this, for this we look upon, this is the 0, sorry, this is the 0, and for this 0 we are going to do the penalties, assign the penalties. So that means the minimum value is 3 and other value is 0, this 0 is there. So 3 plus 0, 3 is there. For this row 0 we assign the penalty, least value is 4, and the other least value is in the column 0. So 4 0 comes 4. So we have to now the case is now a little bit different over there. I'll change. Here it is a 4. Here it is a 4. So there is a two 4s are there. Penalties are there. So it is up to you which penalty you can use. Suppose I use this because same values are there. Now we are going to cross this row and this column completely from the matrix. So now you left with the, that means when you that means this route you have assigned, and route you have assigned, that means A to B. Route you fix and you block, and to block the route, that means you have to remove B row and sorry, A row and B column. Now the remaining is this A C E, A C E and B, sorry, B D E, B D E, yes. And the elements we have mentioned the elements 1 2 0 0 infinity 3 0 4 infinity, we have to mention. Yes. So after that, now what we have to do, again we are going to do the column reduction and row reduction. Okay. And after column reduction and row reduction, because no, nothing going to be changed, because in the row 0 is there, 1 0 is there. In this, now here you are going to check, here we have to check, we have to check, this is, this comes to be infinity 4 4, B infinity, no, this this will be moved and this row will be removed. Only we have left with the B, sorry, A, A, C, and row we have B, D, E. So this matrix we have ACE and BDE, ACE and BDE. We have the matrix, and the cell values we have mentioned as it is. All values we have mentioned as it is. Now again we do the row reduction and column reduction over there. And the column reduction when we do over there, that means in this row least value is, let's say, is 0, so no change. In the row 0 is there, no change. So yes, we have to do this way. This is the row, this is the row, this is the row. So first row we have the 0, that means nothing to be changed, 1 0 0 as it is. In this we check 2 infinity 4, let's check this we have to check. Then we have 0 3 infinity, 0 3 infinity as. Now nothing to be changed. Over there, there is a 2 value, and if we count 2 value, it's 0 and it comes to be 2. It comes to be 2. And now we see column reduction. In the column reduction, there is a 0 is there, no change. 0 is there, no change. 0 is there, no change. So we can see this way. And then we are going to this is the 0, this is 2. This is 0 and 2. Further, this is 0. 0 and 2. 0 and this is 2. Now we have to assign the penalties. Further, we have to assign the penalties over there. We suppose we look upon this. If we look upon this, 0 is there, 0 is there. So we have to assign 0 plus 2. come to be penalty 2. And if I look upon this row, this 0, okay, and after this 3 values there, 3, 0, 3 plus 0, 3. For this 0, look upon minimum value, 4 is there, and other value is 0, so penalty is 4. For this, for this is 0, and here value is minimum 2, 0 plus 2, 2 penalty, there no 0. For this 0, for this 0, this is 0, oh sorry, this, yes, here 0 is there, so the 0 is there, and mean value is 3, this is 3. Now we look upon the maximum penalty. Maximum penalty comes to be this is the maximum penalty. You block this, completely block this row and column, and we are going to remove this row and remove this column from the matrix. So after that, you see our matrix will become 2 by 2. Our matrix will become 2 by 2. I change the value. It is a 0. It is a 0 over here. It is 0 over here. Yes. 0 infinity 0 3. Yes. Now 0 0 infinity 3. Now we'll look upon. We have to do the column reduction and row reduction. Now no need, because 0 0 over there, you see when we do the row reduction, then 0 minus infinity remains same, 0 is there. In this row, 0 and 3, 0 minus 3, no change. In the column we see 0 is there, now here 3 is there. So now we have to, for this column we need to do the column reduction. So subtract this 3 minus 3, infinity minus 3, infinity remains infinity. So at the end we get this 0 0 0. So this way we get the row, yes, 0 0 0 over there. Now this is the row reduction, and further we see we do the column reduction, and in the column reduction we get all the values 0 0 0 over there, because when you subtract 3 it will be 0 over there. Now in the column reduction, after column reduction, what we have to do, assign the penalties. In the penalties we have to assign the 0. In this 0, this 0 is there, the value is infinity, so 0 plus infinity, this is the infinity. For this 0, this 0, this is 0, and the value is 0, so here 0 0. Now for this 0, look upon this value, this in this row the value is infinity, and the column wise value is 0, so infinity, row wise plus column wise add. So which infinity, it is up to you. Now suppose I cross out this value, I remove this, because this is the highest penalty we get. That means we have to fix the root. That means we have fixed the root. We have fixed the root B B C. We fix the root, because we are not going to afford uh, to uh, uh, get the, you can say, our cost more. If otherwise we are going to follow any other route, then definitely we are going to bear the loss. So that means we have to remove this, because we have to block the uh, both ways, from B to C and C to B. So we remove this row and column from the matrix. So only one element will be left, D E, and D to E is 0. D2 is 0. So that means the final root you get D to E over there. Over here. So the root we have C to D, A to B, E to A, B to C, D to E. All roots are where the roots we have blocked, where the penalties are maximum penalties. We have blocked this. From there we get the roots. So that means we starting point A is there. That means A to, first he go B, and then we look upon B. Yes. So then B to C, and then C to D, C to D, and then D to E, and then E to A. So this is our route for the salesman. And if the salesman has a native place, then salesman is supposed native place is E. So that means we start the route from this. Start from this. That means E to A, and after that we know A to B, C to D is there, and then D to E. So that means if the salesman has a native place in the city E, then we start the route over there. But you can see over there, rest of the path remains same. Only we have the starting point different. You can see A, this is there, and then we have to find the cost, and the cost will be we have this route A to B, B to C, C to. Now the total cost of journey will be, now we look upon the cell value A B cell, this cell value A B, cell value A B, this is 2, and then cell value PC, cell value BC 6, and then cell value CD, CD, this is 3, and then cell value DE, 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 this is 5, and then cell value E to A 3. Sum of this to get the total cost of the journey, and this is the optimum value to get it. Okay. This is how we can solve the traveling salesman problem. And if you have any doubt, you can put me in the LP live over there, so that I'll resolve your queries. Thank you very much.